So I've now moved, you can see my background has changed, and I've also done a little bit of refinement on the circuit. So let's point out some of the differences. Firstly, let's look at this circuit. You can notice that this is a specific symbol for a circuit. This represents a P-channel MOSFET, meaning that it's going to switch in a different way to N-channel MOSFET, which is a completely different system. Now, remember, this is of course the set problem. If we switch over and we look at what they actually wanted specified, you can see the symbol is completely different. They wanted the N-channel MOSFET. So this is the primary reason why the answer was completely wrong. Also, I did just a little bit of general tidying up so you can see it just looks a bit nicer now. Zoom in a bit. So we can see here's the P channel. We need to get rid of that one. And what we'll do is place a component. This time around though, we'll actually make a change. We'll use a virtual transistor. This is a level 1 design. There's a couple different levels of design parameters you can use for a MOSFET within the simulation. Now, you can find that we are actually going to be using a different transfer function. So we'll enter this information in. Now, typically you'll be able to enter in some spice. So let's go to our spice and try and enter in something. We'll find that the component that we want to change is, oh, I'll have to run this to update that, sorry. Here we go. Is here, it's our NMOS virtual transistor. We have length and width here, so let's add in KP. So if we click here, it doesn't let you, and it says it must be edited in this schematic. Now, in Multisim, that means that we must edit it somehow here. And okay, here's length and width. It's fantastic to see we have a notification. Let's turn notifications. Oh, fuck. So good. So we have the length and width here. Now we can just change those to the values that were specified. Now let me just grab the length and width. I wrote them down just here. So we have 0.18 micros, and this one will be 18 micros. Now you notice I had KP before, and looks like this is all the parameters we've got. Actually, we can edit the model here, and you've got KP, VTO, and lambda. Lambda is there. So we could use the default values, or in this case, we actually want to set them. So we have to uncheck use default. Now, the VTO voltage threshold was 0.4. The transconductance was 0.05. Then the lambda is 0, and that means that we've got the parameters specified. Now if I just go change component, okay, we'll start and stop that. Now, does this change? Oh my gosh. Everything's happening. Okay, so does this change? The answer is yes. We have this changed. Now it's 18e-7 and 1.8e-5, so that corresponds to what we expected. Then we have also got this section here. We got level 1 that specifies the kind of detail that's involved in the model. VTO is 0.4, KP is 0.05, and lambda is 0. So fantastic, we've got the values in that we need. Now we went away and we did some calculations. So we reset these values to whatever. Now, if I change them to what we want them to be, we'll change them to 20 mega ohms, so 20 mega ohms, and 1 mega ohm, then 3.6 kilo ohm, and finally I might move that up a touch just to make it nicer. And then finally 883 ohms. Now nothing else has changed here. We did add two other things. So we added a on-page connector. So I'll just delete these so I can show how these are added. So we're going to place in schematic. We want to place on-page connector. We'll place it there. This is VI, so let's connect it to VI. And we'll place it again. So place in schematic, on-page connector. Place that one here, and this is VO. Okay, I'll just rotate that. Yeah. Oh. Okay, let's line that up. So now this is these on-page connectors are connected to a oscilloscope. We had the oscilloscope there previously. Now this is an Agilent oscilloscope, so I'll show you how we do the setting up. So we'll delete that. We'll grab the Agilent oscilloscope from there. This, and we look at it. We have 1, 2, and 3 inputs on the side, and the middle input corresponds to ground. So we have 1, 2, 3. Middle input corresponds to ground. Then we have 1 and 2, channel 1 and 2. So then that means these are the channels. These are digital inputs. So we'll just move that across. Then we'll put those in. So 1 and 2. There's no other changes to the setup, so we just start running. And what we'll do is we'll turn the power on for this device. We'll press number 1 is automatically there. Its coupling is DC. And number 2, we need the coupling to be AC. Now we'll also press auto scale. That'll help us a bit. And we should now be able to do a measurement. So we can measure the peak-to-peak voltage of source 1. We can then obviously want to do that for source 2, so peak-to-peak voltage of source 2. And we also want the average of source 2, so we'll get the average as well. Now we can see, let's move source 2 up. Wait. I want that. Oh, move a lot. Getting there. It's got a rather large offset for some reason. I did set it to AC, but whatever. That's life. I did set it to AC. Yeah, it says coupling AC. Oh, whatever. So we'll just keep on. If I just press the down button, it'll do it automatically. It's doing it slowly, but it's still getting there, rather than me having to spin the thingy around a lot. Oh, it's slow. Getting there, getting there. There we are, finally. Great. Okay, and there we go. We have now got our 2 inputs there. We have the quick measure. We can see that the peak-to-peak voltage of input 1 is 5 millivolts, which is what we had set. Peak-to-peak voltage of input 2 is 5.02. So that's 100 times gain. That's exactly what it was designed for. The average voltage is, for some reason, 2.87 millivolts, which is obviously incorrect. That would probably be explained why the system wasn't going well. Just change this to DC to AC. Potentially there was an issue there. So let's see, quick measure. So one thing that we do know is that it's not possible for the this one to be oscillating around 0 volts, but that's fine. We'll go and check this. Looks like it's okay. We can also verify, so I did a quick thing. I made it earlier just to make sure everything would work. So we can see that this is all fine, and this is the same setup. And if we run this one, we'll see that if we quick measure, source 1 peak to peak, and then, whoops, I need to change quick measure. Source 2 peak to peak, and then source 2 average. We'll see that it's more like 10 volts, and that's what we expected. The reason we expect 10 volts is because the resistance is moderately minimal here, and the current down here should be quite low. That represents exactly what we see here, as the voltage is around 9.4, and that gives us an average is what we expect. We can then go back to doing our graphs. We go simulate analysis, AC analysis. We can go analysis output. We can grab, it doesn't matter, so we'll grab VI, the probes, points, so the points here. We can then add an expression for this one. What we might do is to show or to see how well the signals match up. We can grab, okay, we'll add those back. We'll grab V in, but we'll add an expression for V out. Firstly, we'll make it negative, so then it is not inverted, and then we'll divide it by 100. And so it's not exactly right, but it should be quite close together. Now, when we simulate this, this is not exactly what I wanted to see. I think I wanted to go transient, not AC analysis. So, transient analysis, there we are. Add expression, we'll add that one. Okay, we'll remove that one, we'll add into it VI, simulate that. Much better. So, now we have a bit of an offset here. So if we check that offset, let's see if I can grab that value. Add data cancel, add traces from last simulation result. No. This is the offset that we had before. So let's try a few things. Firstly, let's see if we can change how the axis is operating. Trace label, offset, auto separate. No, we don't want to do that. We'll go add 100, probably 9.8 M, 98 M, 98. Let's see. Okay, this is where now? Oops. Have not got our green line anymore. Probably because it didn't like the fact that it's that way, so I put 0.098. See if it comes back. It has not come back. Just say 0. Okay, and then it's completely gone. Okay, that's fine. I'll go back here, and then we'll change it in the main analysis. So analysis, transient, go here, and we'll add, instead we'll put 9.8 volts, which corresponded, should get it from here. So the 9.69, so we'll use that instead. Simulate instruments, analysis, that one, go here, 9.69, minus that one. Simulate that. Okay, there we are. Okay, so we can see that for most part there is minimal difference. I think this one will be due to the fact that the offset is not exactly correct, and the height is because the amplitude is not exactly correct. However, it does show you that the signals are close, that the signals don't appear too deformed, and this is a fantastic kind of result. The only other thing left to do here, I don't know if there's anything interesting there. No. The only other thing left to do here is to do a Bode plot of the system, and then we did that before, but we'll do it again. Last time it came out with negative 25 decibels, and that's because, believe it or not, this system was not an amplifier. So we're going to use these pins to do the Bode plot. We copied them across, and so it automatically updates the name, which is useless, but it's just how it works. So we just edit those. Okay, so now we'll connect that to the positive and that one to the negative. We'll copy the ground across, as they're all common ground. And that one set up, we can open up the Bode plotter. We go run. We should have seen something, but the reason we didn't is because the final value for the vertical axis is was 0. Now we can see something. You can see that at 1 millihertz, the gain is 11 decibels, and we go up to 8 hertz, and the gain is 40 decibels. If we continue into the megahertz and gigahertz, that doesn't change at all. So why don't we just set this as 50? We'll go back here. We'll go to 10 hertz. So that's easy. The final is 10 hertz, and then the initial we'll set as probably just 1 hertz would probably be fine. 1 hertz. Yeah. Then the minimum is more like 11, but let's just check that exactly. Oh, I should change that to 1 millihertz. There we go. That looks much nicer. Let's set that to 10. Maybe that'll look a bit better. 0. Yeah, that looks nice to me. I like that. I like that plot. Okay, so that is this part of the question. The negative 3 decibel part, well, that's kind of hard to determine, but the maximum gain is around 40.141 decibels. So that means 37 decibels will occur at approximately here, and so 464 millihertz. That's a strange result, but if there's something that you care about, that's what you care about. If not, well, fine. What you could say that represents is that you can amplify a signal with the specified gain so long as you're operating at least 1 hertz. So that's pretty good. That means you can amplify any kind of voice, etc., or any audio. So that's a nice little bit. Now, we're also asked to do a few little modifications to the circuit. So why don't we, we'll save this. Now we'll save as B. So we want to replace that, and I know it's open. So let's use B. I'll save as again. CS B. Yep, I want to save that now. Okay, so that's what we want. Verify. So we want to run it for 3 different voltages. Compare and discuss. So we want to look at the output voltage for those 3 inputs, attach them to transient simulation results. Okay, fine. So we'll change this. Remember, it was, for some reason, it's divided by 2. We could get a little bit of insight into that, but to me, it doesn't really matter that much. So move that away. You are currently running at 5, so we want to double that to 10. So that means I should put 5 here. I should also just put a little oscilloscope in multimeter, just to ensure that we're running at what we expect it to be running at. So we open up this multimeter, we can click run. What we can see is AC, get apparently 0 volts at the moment, which is interesting. So that is particularly useless. We'll use a Tektronix oscilloscope again. I like this one because it's rather simple. And this one is an analog only one. So we'll go this one. Channel 1 should be on. Change the seconds to a division. We'll change the volts per division. There we go. Oh, I think we've gone too far. Perfect. Now we'll go utility. Oh, sorry. Measure. Channel 1, type, frequency, period, mean. That means around 0. Fine. Peak to peak, 10 millivolts. So that's exactly what we want. At 10 millivolts. Now we'll change this to a AC simulation. So we'll go analysis, transient analysis. Instead of this one, we'll just use that one. VI, VO, add. And then we'll go simulate. So I don't want that anymore. I guess I can remove that entirely. Do this one. Sorry, analysis, transient. I don't know what VN. It's not particularly interesting to me. Simulate. And then what we can see is a bit interesting. As the voltage rises, it becomes clipped here. And so that's an important change. That's what we sort of predicted a bit earlier would happen if we want to try and increase what's happening. Or that it can increase the input. So I actually want to just try and close these. So clear pages. I want to get rid of, check all except for this latest one. Right. So that is for 10 millivolts. So let's see if I can change this. Transient analysis, 10 millivolt. Great. So I'll just confirm that we can save this as something or other. Oh, let's see if we save it as something that's not a silly file. A CSV, yep, that's fine for us. So we'll, why don't we edit this again? We'll cut that, or we'll put that there. And now we'll save that as a CSV. And then we'll also call this Q2. So Q2 transient analysis. Yes, that's fine. Then we'll obviously repeat this. So we were to double the voltage again. So that means I should set this to 10. I'll run that. We'll ensure that this is now 20 millivolts peak to peak, and that's exactly what we're asked to do. We can now run an analysis, transient analysis once more, simulate, and again we can see how this is happening or what's happening. We'll change this one, grab the name again, oops, go to that one, that one, and now this is 20 millivolts. So what that's clearly showing us is that there is a limit to the voltage that you could put into it. I assume that you could actually reduce the voltage. So what we would probably want to do is to have a system which actually has a lower VGS, but for some reason this current setup is not designed to do that. Okay, so transient analysis, 20 millivolts. Then we can change this. We need to do 30 millivolts, so we want to add that to 15. We'll run it. We'll check that it's 30 millivolts. Yep. Actually, now let's go. We'll simulate instruments. Sorry, every single time I click instruments. Okay, simulate that one. And you can see it just keeps on going longer and longer. That's just because it's clipping harder and harder. 30 millivolts. Okay, and then save as 30 millivolts, CSV, save. Okay, now actually what we can do, as I saw before, is we can overlay some traces. So what we can do is overlay this one and this one. I think this would be fine. Let's try this one. Nope, I do not want the Bode plot. Try a different one. Okay, we'll try. Oh no, we'll go back here. Go merge. Let's try this one. Yep, okay, good. Merge, and then we'll try this one. Good. That's what we wanted to see. So let's try to change these names. So one is going to be VO, and then it's 10 millivolt. Apply. Oh, let's try VO 10 millivolt. Then we're going to grab this one and go VO. Oops. VO 20 millivolt. This one, we're going to go VO 30 millivolt. Right. So that looks quite nice. We can quite clearly see what's happening here. We'll save that as a graph. No, a graph. We'll save that as that one. So Q to all CSV. Yeah. Now we can confirm that was all fine later on. Now we wanted to remove C1, and then so as B, this is B. We're just going to remove C1, this capacitor here. Let's do that. Now we'll start simulating once more. We'll just simulate backwards now. So we'll go as transient analysis. Go simulate. That's fine. Actually, we can do. Let's try something. We'll try what's called a parameter sweep. See if we can get all these to happen at once. So we want to selected variables for analysis is the out, and analysis parameters. We want to change a voltage source. We want to change voltage gen positive, C, source negative, XFG. Okay, so this is positive and that's negative, so I want to go positive. Then I want to start and stop, so I'll start at 5 millivolts and I'll stop at 15 millivolts, which corresponds to the ones that we're wanting. Oh, sorry, I wanted 2.5. And then, actually, we'll probably just do a list. So, don't know if I can switch that. 5. Okay, 0.05, 0.05. 0.015, if I'm correct. Let's see. So 5, 10, 20, and 50 and 30. Okay. So then that's 2.5, 5, 2.5, 2, 5, 5, 5, 10, and 0.25. So that should be end up with 50. We can always check if we can make sure that we are converting millivolts to volts correctly. Let's see what we've got up here. Volt to millivolt. So if we want to go, actually we'll do 50 MV to V. We can check, we'll see that we have not added another, we need to add another digit. So we'll have, this is 0.25, then to get 20, 10, that one, and that one. So we will want transient analysis, output, device parameter. So I am unaware as to why that doesn't want to run. So let's say OK, simulate analysis, parameter sweep. It does not want to run. Transient analysis, edit analysis. Seems fine. Output. Have just that one output. AC. Let's look for device parameter, or parameter, B source, B parameter, nope, circuit parameter. Okay. We'll try one other way. See if we can find what that circuit parameter thing is. Well, we'll just give up and do this. So we're going to go from 2.5, will result in the peak-to-peak voltage being 5. We'll now go simulate analysis, so this is going to be incredibly boring now. So now we want to pull this one. I do actually want to close all the pages again. Clear pages, check all except for that one. Okay. This one is called I'll call it question 3, 5 volt. Apply. Probably change that there as well. Apply. Then, based on what we observed before, we can just close that and go 5. Go 10 millivolts. Great. Simulate analysis. Transient. Simulate. No problem. That Bode plotter comes up every single time because we've still got a Bode plotter in here. So we'll delete that Bode plotter. And well, now I'll do the next one. So we wanted 20 millivolts next. So that means we want to put that as 10. So then run that. That says it's now 20 millivolts. Fine. We'll go simulate. Transient analysis, simulate. Okay, now I'll just close the Bode plotter one. I don't want. Okay, I would say this is, call that that one. This is 10 millivolts. Remember. Copy that there. Apply. Then this one was 20 millivolts. Do that to there. Don't want to cancel. Apply that. Then we wanted 50 millivolts, so that means to be set to 25. Run that once more. That says it's now 50 millivolts peak to peak. Stop that. Go simulate analysis, transient analysis. Simulate, easy peasy. Name of that one. There. 50 millivolts. Copy that, paste it there, 50 millivolts, apply. Easy. So now we would like to overlay all these plots, but I'll first save them out just in case. Save as Q3 CSV. Yes. I'll as CSV. Yep. I'll save as CSV. I'll save as CSV. Great. Now, we'll just take some screenshots of this as well. So I want to go Control Alt that one. No, this one. This is a screenshotting tool from the Mac. One. Yep. 2. Oops. Wrong one. 3. 4. Right. Now, we will overlay these. Overlay traces. This one. And overlay the next one. And overlay the next one. Ah, hold up. That should be the 3 that I wanted. I think I need to add this one, the 20 mil. Yes, okay, perfect. So, the red one, I should have checked that before. Okay, let's close these pages. New pages, these merged ones. Okay, I'll actually give them a name. So I'll call this VO5MV. I'll call this one VO10MV. This one will be called VO20MV. Called VO50MV. Now we can merge those, and hopefully we'll see that they copy the names. Oh, perfect. 10 and 20. Great. We have the ones that we want. Now that's quite interesting that the amplitude continues to rise, but that's exactly what I expected. Also, we can see it's not clipping and has actually quite similar average voltage overall. It's a good result. Right, so what we want to do is we'll save that one. Oops, I don't want to have those points on it though. So let's try and... No, doesn't matter. Ooh, don't want to merge one. I want to just go Q3. Okay. Why did that not change? Oh, right, of course. Okay. Analysis, we'll screenshot that up. That's Q3. And now Q4 asks, that was Q3 and Q4 plot frequency response of the amplifier. Well, obviously we've done that a few times now. We'll grab the frequency response though in that nice plot format. Let's go to Bode Plotter, we'll put it right there. And we'll in legs. There and there. We'll then set that to what we knew was 50 11, and from that to maybe 1 gig. 100 megahertz, that's fine. It's the same thing. Now I wanted to change that back to the right nav value, so 2.5. Obviously we don't femtovolts, we want millivolts. Oh, that will correspond to 5 millivolts peak to peak. Exactly what I wanted to see. We'll check that this is correct. So now we can see that there's an issue here. Let's bump obviously. The issue will be around the fact that it is blue. Interesting. What is the value here? It is always going to be 11. If I put it up to 500 gigahertz, it shouldn't do anything different really. Yeah, perfectly fine. It's showing us that we have a consistent gain of the whole system. So if I put this as to 20, 15 even, it's going to be exactly the same. There's going to be no difference between linear and log here. 12, 13. That's one in the middle of the page. So from 1 millihertz to 1 gigahertz, it has a very flat response, which is perfectly fine. We'll now go simulate analysis. Back to this transient analysis. Simulate for a second. We'll grab the Bode plotter, and we'll see that the gain is consistent. Now I'll want to put that in the middle again. So left axis, we'll put that 11, and then we'll 13. Whatever range, we'll put that the same. And then we can see that also the phase is perfectly fine. Actually, we can see that it's 180 degrees. So what we do is that it's 270, negative 360, positive 360. That is pretty good. It shows us 180. So we'll screen out as well. We'll screenshot with the right button. And then I'll also just mention this is the Q3 Bode apply. Okay, that will be much better much clearer. And then that is perfectly acceptable. I'll put back this capacitor, and then we'll just be able to do a comparison between the two. Go there, go there. Now, that should be fine. Go simulate analysis, transient analysis. Simulate, we have the Bode plotter for here. See that we've got the same result. So that's not what I expected. This is what I expected. So 50, where this is more like it. And I'll push it to more like 100 hertz. Perfect. Go sim analysis, transient. Should have come up with that one. Good. Access properties, auto range, apply. Excellent. And do the same thing. Wonder if we can auto range the bottom axis, range. Okay. Didn't make any difference, so I don't want terahertz. I just want hertz. Thanks. Be great. And then they'll do the same for here. This axis, so I want just 500 hertz, terahertz again. And then I'll change these from apply that. You can see there's an interesting bump there. I will change this Q1 Bode. Okay, screenshot that out. Perfect. That looks like we're all good. There we go. Done some little amplifier circuit with a gain of 100. Excellent.